Hello, people. Admit all. Let's see here. Templeton, co-host. Yeah. Okay. So, hello, Logan. Hello, Katrina. Let's see. Katrina's asking about the video thing. I'm still working on it. I've been going back and forth with some district people about it, and so still working on it. These are all being recorded, so they are captured. It's just they're big enough that they're unwieldy. So I am working on it. Okay, I am working on it for sure, and eventually I should be able to post it. Okay. All right. Today, let's see. I guess 3-ish things. Thing one is to go over assignments. That thing, right? Thing two would be just a brief introduction of differential equations that that are proportional. See, a differential equation growth, right? The rate of change, the derivative, is proportional to how much stuff is there. So the more stuff is there, the greater the growth, if that makes sense. And so we'll see, what does that mean? Okay, we'll take a look at that today. Okay, what kind of growth does that mean? And there won't be an assignment associated with that, but it's just to kind of oh, there we go. That's how it works. And then a bigger chunk will be looking at something called slope fields. Slope fields. And so we'll take a look at that today too. Okay, and then the assignment. Tomorrow there'll be I'll give you some AP questions that that are about differential equations, that focus in on differential equations, and you can solve them. Okay, and yes, 4 and 6, definitely. We'll figure that out. 4 and 6. 4, 6. Yeah. Oh, nice. Okay. So general solution. So for a general solution, that's one that will have plus C at the end, or or in the middle of it. So it is basically a family of functions. Because remember, if you have a derivative just explains the slope, the rate of change of the original function. So you can have two separate functions have the same rate of change if they're kind of vertical shifts of each other. So think about a parabola that's up here versus a parabola down here. Their slope profile is identical, right? But just one's higher or lower than the other. Okay, so that's that would be a general solution, plus C, meaning it could be anywhere. A specific or particular solution would be one where a point on the original graph, and that will determine what C is. Okay, so and so that's the difference between 4 and 6. 4 is asking for a general solution, so you'll have a plus C in there, and then 6 is looking for a particular solution, right? Where when you put 1 into your function, you should get out E. Okay, so yeah, let's chomp on those. Okay, so we're doing 4 first. Okay, so before we start, if I look at this differential equation, I see it's dy over dx. And so if I multiply both sides by dx, dx is going to end up over here, right? And dy will just remain over here. That means I need all my x's over here, all my y's over there. Okay, so usually it's, well, almost always dy over dx. So wherever dy is, that side is kind of where you put y. And then dx will be on the other side of the equation, okay? I'm trying to think of when that's not true. And I can't think of one right now. Okay, so already, because dy is in the numerator, it's going to stay on this side. Dx is going to pop over there, and when I multiply both sides by dx, and then we're good. Okay. All right. So I'm going to multiply both sides by dx. And then those cancel, basically, right? So now, let me see what I have. I have x minus 2 dy 2y dx, okay? So again, these differentials, dy dx, these are bullies, right? This is saying y is over here, y is over here. This is saying x is over here, x is over here, right? And so I gotta move this over here. I gotta move the 2y over there. I can just leave the 2 there, I guess. Or I can bring it over here, okay? So does that make sense? I have to move those to the side. So if I do that, move this over here, it'll have a 1 over 2y dy. I move this over here, I have to divide by it, right? 1 over x minus 2 dx. How's that? Toma, yes. Okay, so here I've separated the variables. Okay, and this is what you have to do first. You have to separate the variables. Tomorrow, when I give you the scoring guidelines, we're going to give you some. Oh, hold on. I'm admitting Fran. Hello, Fran. We do the AP questions. I'll give you the scoring guidelines, and if you don't separate the variables, the penalty is harsh. Right, you'll see it. I'm not going to give it away now, but it's harsh, right? If you don't separate the variables, you're hosed. Okay, so we got that now. So we can integrate, right? This is all in terms of y. This is all in terms of x. That's great. So I'm going to pull the 1/2 outside like this. Easier, right? We're okay over here. So how do these integrate? Well, this one over here on the left-hand side would be a 1/2 natural log of absolute value of y, right? Over here, this will be natural log of absolute value of x minus 2 plus c. So again, you have an integration constant. You could write them on both sides, but then if you subtract one from the other, you get another constant. And so that's why you can get away with just doing one constant, okay? So just plus c over here. All right, now what? Well, I want to solve for y, right? And that's what my whole thing is, get y by itself, because that's the solution to a differential equation is a function, okay? And so y equals, we'll put it in a function form. So before I move things all together, I'm going to move the 1/2 over here, right? And so that would be natural log absolute value of y equals 2 natural log y, sorry, of x minus 2. And then I would multiply this by 2 as well, but 2 times c is yet another constant. So you're okay with just keeping it c, all right? You're okay with just keeping it c, all right? If you want to put 2c there, you're not wrong, okay? No, you can move it over at the end, but what I'm going to do here, this is a log form. And remember, I'm going to put this in exponential form, okay? I'm going to move this computer back so we can see more. Okay. So right now it is in log form, and now I'm going to shift it to exponential form, okay? So if I look at this part right here, my base is e, because natural log is base e, logarithm, right? And so let's see this over here. So I'll go right here. So now I have a base e right? Base E, and this big nasty thing is my exponent, right? Remember, a log is an exponent. So here's my exponent. And what does that equal? That, right? So this is the log form. This is the equivalent exponential form. Okay? So, I mean, I really didn't do any calculus here. I think I've done, my calculus is done now, actually. What I'm doing now is just making it into a function, all right? My calculus is done right here, right? And now I'm just doing algebra. I mean, it's a pain in the butt algebra, but it's just algebra, right? You can't see what this says over here? Yeah, okay. Let's see. I'm gonna go darker. Yeah, okay. So now, I want to solve for this, okay? Now, if now you just did plus or minus over here, you'd be right, actually, okay? I'm gonna be calculus-y here and do some more type of solving. What we did yesterday, actually, when we did the intro. So this, remember, E, when you have an exponent that is being added, it's the same thing as multiplying with the same base. Okay, so where does the 1 over y come from? Right here? Okay, so so I need to bring the y's over here, right? Because the dy establishes this is the y side, right? This is the y side because of dy. Well, to do that, I have to divide by 2y. So I divide by 2y, I get 1 over 2y, but then I took the 1/2, I put the 2 out here. So that's where this comes from. Yeah? Yeah, okay. So now I'm going to split this up into 2 chunks, right? This will be E natural log of x minus 2 times E to the C. Right? Okay? So now E to the C is just another constant, right? E to some constant is yet another constant. So you can call it, K, you can call it Q, whatever. So I'm going to call this thing Q. I don't know, whatever. Okay? Now I've got this Q times E to the 2 natural log of x minus 2. Okay, so now if you notice, I have E right here and the natural log as its exponent. Okay. I'll get to that question in a second, Katrina. So you know one of the E to the natural log of x is x, right? Can you see that? Yeah. So this is one of our about E and natural log. Okay, so how do we incorporate that? Well, this doesn't have a coefficient. This does, right? And so I can use the throw up property, right? So we write it like this. Right? So this coefficient in front of a logarithm can become an exponent. That's the throw up property, okay? So now I can use this identity now, right here. Q times the square of, you know, I can take off the absolute value things because when you square it, it goes away anyway, so I'll just do that. Okay? Equals that. So now I'm to the point where I can do the plus or minus. So y is positive or negative Q x minus 2 squared. Okay, so if this is, you know, I have not seen on the AP exam them ask for a general solution. I've seen them almost exclusively look for particular solutions. Doesn't mean it couldn't happen. But if this is, so let me show you where you could just stop. Okay, so this is kind of, does this match your answers? Okay. No, you can use whatever you want here. But on the test, where you could stop, here's what you could do. See this stuff right here? Because all I did from here on down, was simplify this side, right? I just simplified this side over here. That's what all I did to down here, except for the plus or minus. So what you could do from this point right here, if this were really the question, you could say, oh, well, y is going to be plus or minus e to the 2 natural log. And that is okay. Right? This is a full credit answer because all this is simplify. You don't have to simplify. Yeah, you like that better. Oh, okay. So the reason why the Q would drop the plus or minus is because Q is any kind of general constant. And so you know, plus Q or minus Q is another constant. Okay, so that's why you can technically drop it if you want. Okay. So this one was a little bit more challenging because we had double natural log. I mean, what a pain. What a pain. Okay. Use a different C instead of Q. Oh, right. A big C in front or something like that. Yeah, sorry about that. They kind of just bundle, they keep bundling constants and still call them C, which is okay, but it can get confusing. So agreed. Agreed. So are we okay on this one, number 4, before we tackle number 6? Yup. Okay. All right. So let's do number 6. Ugh. I just looked at it. I think we're gonna get something similar. Dang it. All right. So I'd have to say, in general, friends, the ones that are the hardest when you're solving differential equations are when you get 1 over your variable. That's going to integrate to natural log of the absolute value. So you introduce more layers of complexity. Natural log is a layer of complexity. And you also introduce absolute value, which is another layer of complexity. And so that's why these can be more challenging. But remember, not all differential equations will give you an integrand of 1 over x or 1 over y, right? Some of them just give you a power function, and then you're psyched, okay? And then you're like, yeah, okay? So, or an exponential, right? So that's good news. All right, so let's do number 6. Okay, so this right here, this initial condition is code for, oh, this point is on the graph, okay? And that will become more important to us today when we're dealing with graphs. So slope fields are actually graphs, and so this will become more important to us today. All right, so what I see here is dy is on top on this side, so that means this is probably gonna be my y side. The x is down here, so it's going to jump over there. Okay, so first thing to do is to multiply by dx. Those cancel. So what I get is y dx negative 3x dy. Okay, grumpy. I get grumpy because there's your y. Y is over there. X is over here. Okay, so I've got to divide. You know, I got to divide by y, which is put y in the basement over here. And I'm going to divide by x. Okay, and I'm going to leave the negative 3 there. Before, I remember it was a 2y and I brought the 2 over with it, but I'm going to leave it here this time. And just because I'm just showing you you can just leave the constants where they are. So what I get if I divide by x, I'm actually dividing by xy, right? So I get 1 over x dx right here, and then I get negative 3 over y right there. Okay. So I left the negative 3 over here. I'm dividing by what is effectively the common denominator, and then this is what I get for I'm separating the variables. Okay. So now I can integrate. So I'm bummed because I got x and y in the basement again, right? Again. So before I do that, I'm going to take the negative 3 out, right? So now I have 1 over y. All right, so over here, natural log. Okay, and I'm going to put the plus c up. Nice, Mr. Kuhn. With the x. And I always do that because I have to solve for that y. And so that if I put the constant over here, I have to move it over here anyway. Right? All right. So now I guess I have to move this over here anyway. So I guess I could have moved it with the x, but negative 1/3 natural log. Okay, so again, you can, if you want, divide this c by negative 3. But again, that again is another constant. A constant divided by negative 3. Oh, it's another constant. So you can leave it like that. No penalty. It's all good. And now I can rewrite this in its exponential form, right? Oh wait, I'm stopping. Stop. Time out, Mr. Kuhn. Time out. Okay. So before I do this, what I typically do is if I have a point, right, I've now integrated, I'm going to solve for c right now. So if you look at the little the chart that Gary put together for this section, like it's right at the top of the first page, right? Here's your procedure for solving differential equations by separation of variables. It says that you can either solve for y and then get c, or he says they're interchangeable. I almost always solve for c as soon as I can, okay? Because it's just so much easier. Because remember before we had to do, oh, the c is an exponent, and so e to the c is another constant. So that's what you end up having to do if you leave it, okay? You can if you want. So if you put a c over here, you're going to have to move it over here anyway, right? Because you're going to have to solve for y. So if you put them on both, right, you're going to have to subtract 1. Right? So if you have a c over here, you have to subtract it over here as well. And so a constant minus another constant is still a constant. Okay, so I always put it on the x side because I have a choice. And so that's what I do. Okay. Okay, so I'm going to solve for c. I'm going to use my initial condition. So I'm putting in 1 e, right? So negative 1/3. So substitution. All right, so I put in 1 for x and e for y. Okay, so natural log of 1 is just 0, right? So this is 0. So I just have c over here, and the natural log of e is just 1. So c is 1. Yay. Okay. All right. So now I can take this equation and improve it. So negative 1/3 natural log of x plus 1 equals natural log of absolute value of y. Okay, looks like you can see that. Okay, all right. So now I've got a value in there for C. Now I can, now I want to solve for Y. So this is in its log form, right? Log form. I can turn it around to be in my exponential form. So how do I do that? Well, my base is E, right? Natural log is log base E, is an exponent. So here's my exponent. Right? This whole thing is my exponent. Right? My exponent equals that. So what I've done here is that is the conversion that you learned in Algebra 2 when you first learned about logs. Okay? All right. So now let's look at this. So right now, if you wanted to, you could just do the plus or minus thing and then decide which one's right, plus or minus. Okay, so you could do that right now. Or you could probably do what your scoring, or sorry, your key does, and figures out, simplifies this a little bit. Okay, so I'll do that just to kind of say here's where the key is going. Right, so I'm not done yet. The C is E, we'll be fine. 1 second, I'll get there. Okay, and so remember, we're adding two things up here, but this is in the exponent. So I could rewrite this like times e to the first, right? Right, when you add two things, right? It's like multiplying with add two exponents, you're multiplying with the same base. That means times right there, times e. So that's where this e comes from, right? That's where this e comes from, okay? Ah, yes. So if you want, you can say e times e to the -1/3 natural log of x. Okay, so we still have this y over here. So if I take away this absolute value, I got plus or minus. Now, one of these, plus or minus, one is right, one is wrong. Okay, one is right, one is wrong. So how do we determine which one is right? Flip a coin. Yeah, no. When we put one in, we get positive e out. Okay, not negative e, positive e. Okay, so let's just kind of put one in here for ourselves. One right there for x. Okay, that means the natural log of 1 is 0. Natural log of 1 is 0. So my exponent is 0. E to the 0 power is 1. So 1 times what will give me e out? So this has to be the positive e. Right? If it's negative e, I'll get out, and if it's negative in front, I'll get out a negative e as my result when I put 1 in. I need to get out a positive e. And so this is what we want. Okay? Okay, so you could have, at this point, I'm going to back up here a little bit and said, oh, once we got here, we could have said, oh, I'm going to, let's see, take these off and do the plus or minus right there and decide which one it is. You could have decided back here, right? I knew the answer key probably had a coefficient in front, so I wanted to go through that and just explain how that coefficient came to be. But right here, this is a fine answer as long as you say, oh, it's plus or minus, which one is it? It's plus. And that is a fine answer as well for a particular solution, okay? If it's a general solution, you don't know which way to go, plus or minus, right? Because you don't know anything about an initial condition. So you have to kind of look at both of them. It's either plus or it is minus. It can't be both because that's not a function, right? And so this is fine or this is fine down here. So what's circled up here or this last line, okay? So you can see that when you get, the form 1 over y that you have to integrate, you get a big old box of worms, right? I mean, it's doable, but it is kind of a headache. because you have to go through, you have to take off the natural log, which means you have to put it in exponential form, and then you have to contend with a plus or minus. Right? That's just added layers of complexity. Okay. Again, not extraordinarily difficult because you've looked at this type of stuff before as far as plus or minus and which one is it. But nonetheless, it's when you put them all together, it's an extra challenge. Okay. So how's this one, number 6? Feeling okay about that one? Okay. Anything else on this one? I only saw 4 and 6. How do you know C is inside? Oh, number 2. Well, see, on number 2, as soon as I integrate, that's when I tack on C, right? As soon as you integrate, that C is called the integration constant, and so that's when poof, I introduce C into my equation. Do you want to go through it, Trina? Sure. Alrighty. What do you mean? Well, let's find out here. Or are you, is that the Justin Bieber song, Enders? You like that? Let's see. So here's dy. dx is down here. That means dx is going to end up over here, right? So the left-hand side is going to end up being my y side. This is my x side. So okay. So I like the looks of this right here. I mean, that's nice and cozy. That's good. Right? This is the y side. That's the x side. So I got to get e to the x over here. So I guess I would divide by it. So what you get is 1 over e to the x right there. And then y dy right there. Okay. So let's integrate. Okay. So this integrates to what, 1/2 y squared. And over here, I would kind of write this as e to the negative x, right? Right. That's equivalent 1 over e to the x. Same thing as e to the negative x. And so its antiderivative is going to be e to the negative x with a negative out in front. Okay. How come? Well, the hook-on factor is going to be -1, right? And so you're going to need a negative out there to compensate. Okay. So if you're unsure about this right here, you could always derivatize this side, right? And see, do you get that? And you do. Right, because you would derivatize the negative x, get a negative, and it would cancel with that negative right there. Get that. Okay. So this is where I put the c in right now, because I just integrated, and then you just integrated. Now you would put the c in as soon as you integrate. Okay. So let's just finish this one. So I have to double everything. Get rid of that. So -2. E to the negative x. And again, you can write 2c if you want, or you can just write another c, or put a k in there, or put a d in there, or whatever. It's just another constant, okay? And then lastly, it's plus or minus the square root, right? Okay? And so your general solution, one of them is the positive root, the other one is the negative root, okay? You can't just say plus or minus, because that in of itself is not a function, right? if you put one thing in and you get the positive root and the negative root, positive root out and the negative root out, that's not a function. So you would list them separately. Okay, so there you go. Super. Okay, anything else before we take a look at one other thing? All right, moving on. Let's see. So here's what we're going to take a look at. I'm going to erase all this stuff. Okay, so one differential equation if you could have a rate of change is proportional to okay, the rate of change is proportional to the amount of stuff there is. Okay, so amount of stuff. So typically the amount of stuff might be like population. All right, so if you've got more cockroaches, the more cockroaches you have, the greater the rate of change of the population is. So as more of them, the population rate of change goes up. Okay, so as you get more stuff, right, the rate of change is escalating, increasing. Okay, and so this is how you say it in words. This is how it would look like as a differential equation. The rate of change is proportional to, that's a proportionality constant, the amount of stuff there is. Okay, so K is the proportionality constant. So like 5% or 3 or whatever, it's some number, okay? And so this is a basic model of growth that you might see on the AP exam. It might say, hey, the rate of change is proportional to the square of how much stuff there is, or is inversely proportional to, then you would have y in the basement. Most common is directly proportional, not inversely proportional, or varies with the square of the population or whatever. So this is the most common right here. Okay, so if we were to solve this, okay, if we were to solve this, what would it look like? Okay, so this is effectively section 8.2, but there's a lot more stuff in there that you just don't need. And so you did a lot of that type of stuff in pre-calc, actually. And so once we get our answer here to this differential equation, our solution, then we'll talk about, okay, so where did you see this in pre-calc? Here we go. So to solve this, I need to separate the variables, right? X is on the bottom here, so I want to multiply both sides by dx. Nice dx, thank you. So those go away. So I have dy is equal to k y dx. So obviously the y's go over here, right? X is over here. I don't have any x's, so I just leave the k there. So 1 over y dy equal to k dx. Okay, so I've separated the variables. There are no x's here, so I have a constant over there. But I can take care of that. So when I integrate, this is going to become our old favorite, that, right? It's our favorite. And over here, if that were a 4, how does 4 integrate? As 4x, right? So this is k will integrate as k times x. Okay, so again, if that were a 10, that'd be 10x. If that were 2, that's 2x. If this is pi, that's pi x. Right? So a constant will anti-derivatize to a linear. Okay? All right. So now what? Well, log form, let's put it in exponential form. So my base is e. Here's my exponent. That's a c. Huh? And then that. Okay. So here I've got e. I've got the sum up here again. The sum of two exponents. Okay. So e to the c again is a constant. E to a constant is another constant. What we call it before? Q. Let's call it q. Okay, and then we can do the plus or minus thing. So if you remember, one of you pointed out that they dropped the plus or minus because it's like, it's just a constant, right? And so plus that constant or minus a constant is another constant. And so you could write it like this. So this is your basic model of exponential growth. Oh, how do you know when to split it up, Katrina? Let's see. It's typical in like in most math books to split it up, and instead of having some kind of like simplifying your exponent, if that makes sense. And if you can pull things out of your exponent, that's generally what a textbook will do. Okay, it's not wrong if you don't, but it's conventional to do so. Okay, yeah, it's conventional if you can grab some sort of constant, split up your exponent. Okay, it's not wrong if you don't, but it's more conventional if you do. Okay, so when numbers, yeah, when there's addition up here. Yeah. So this right here is your exponential growth model, or it could be exponential decay. Where did you see it? Well, in pre-calc, you probably did some stuff with half-lives, right? Exponential decay, like, some radioactive something has a half-life of 10,000 years. How much will be there in, 5,000 years, whatever, right? With money or with populations, exponential growth. The population is doubling every 5 years. So if it's this much now, what is it in the future? And so you worked with this in pre-calc and probably algebra 2 as well. Okay, so that's what this differential equation, where you have a rate of change proportional to how much stuff there is, whether it be money or cockroaches or some sort of isotope, right? In chemistry, this would integrate to an exponential model all the time, okay, if it's directly proportional, okay? And so sometimes you might have, as part of your preamble question, it might say something like this, right? And then give you more information. And so what you know is that it will integrate to an exponential model. So you don't have to go through all this to get there, right? If you know this, you can go straight from here to here and say, oh, this means that my solution is going to be an exponential model, okay? And that's okay. I know that's okay. If you want to go through all this, that's fine. But you can just go from here to here right away and just say, I know that it is this type of differential equation will have as its solution an exponential model, okay? And then you can just start working from here, okay? In general, they don't have a lot of those because now once you get here, it's pre-calculus, right? Or even algebra 2, right? So they don't have an excessive amount of questions. questions that go over this. That's why we're just doing it. Oh, wow. Mackie. Mackie, you're late, dang it. All right. So this is it. This is all you need to for this one. So this is 8.2, and then it gives a bunch of pre-calculus work to do. So I thought, I'll spare the pre-calculus work, and we'll get into slope fields. Okay. All righty, slope fields. So this is 8.3. I put it. No, I didn't do 8.2 because we're not doing 8.2. This is basically 8.2. This is the heart of it right here. So 8.3 is what we're doing today, and I posted that yesterday, I think. So 8.3 is in the post from yesterday. So you'll want to take a look at that because that's what we're going to do next, okay? And I'm actually going to use the stuff from the text. Okay, so slope fields, page 167, okay? So slope fields are a really interesting thing. Number one, they look dang cool. They're kind of a pain to build. So we are going to we're going to take a look at a couple. We're going to look at example 1 and 2, which are based on the same differential equation. Okay. So the differential equation is negative x over y, okay? And so the key thing to remember here, dy dx is a rate of change, right? It's a slope, right? So, I think that ran out of paper. Oh, you did? Okay, sorry. Let's see. So it's a slope. Dy dx is the rate of change of the solution curve, okay? And so we can use that fact to find, hey, if the solution goes through this point, if the solution curve goes through this point, what would the slope be at this point, okay? So this just becomes basic arithmetic, to be honest with you. And it's like, well, how is this calculus, right? If I'm just plugging things in and doing something that a freshman would do. Well, remember, this whole thing about calculus is based on slope, right? And that's what freshmen do as well, right? So a slope field would, in general, be like like the XY plane, XY coordinate system with a bunch of whiskers on it. And all the whiskers have a certain slope depending on where they are, okay? So how do you determine the slope of that whisker? Well, what's the differential equation? The differential equation tells you what the slope is. So for example 1, we have this as a differential equation. Okay, and it says find the slopes at these, 4 different points. Okay, so not too hard to do. So at 3, 2, the slope would be, right, x is on top, so it's 3, 2. So the slope at this point would be negative 3/2. So downhill, right? Negative 1.5. Okay. So that's just basic substitution, right? The slope at negative 1, 3. So negative 1 goes on top, 3 on the bottom. So this would be 1/3. Okay. So you just plug those values in and you get your slope value. Okay. If the solution curve goes through that point, that would be the slope of the solution curve, okay? So without, you know, I don't need to do C and D. Why can't you find slopes when y is 0? If you look at your differential equation, if you put a 0 down there, that you don't have anything, right? You got nothing, okay? Negative whatever over 0 would be undefined. Now, you could go vertical there, but you know, with slope fields, you don't need to go vertical for an undefined slope. Okay, you can just leave it off. And in general, they don't ask you to find those slopes. Okay, so the College Board on the AP exam won't say, hey, find the slope at a point that would give you an undefined slope. They leave those off. So again, you'll see that tomorrow. Yeah. Perfectly said, Adele. Look at her comment. Okay. So I'm going to, wait, where is it? I have a prop. So this is in your book, but I wanted to make it big. Hey, there we go. So this is the slope field associated with that differential equation, okay? So we can put some of these on here. So 3, 2, oh, it's already on there. So this little whisker right here at 3, 2, 3, 2 has a slope of -3/2. This little one right here. So you can see this is in your book as well, okay? Okay, this is in your book. -1, 3, -1, 3 has a slope of 1/3. You see that? So this little whisker here has a slope of 1/3. Okay. Let's find one of these and draw it in. Okay. Let's draw this in. Which one should we do? Let's do that one. Okay. So this is the pinky here. That is -1, -2, right? Right? -1, that's the X and Y coordinate. So I'm going to plug that in. So it's the opposite of -1 over -2. So is that 1 over negative? So it's -1/2. So if I was going to draw in, let's see, I guess I can do it with this. Draw in the slope -1/2. So it's like, okay, how do you do this so it looks proper, right? Well, you just want to make sure relative to the things around it, it looks okay. So -1, -1, 2. So in other words, my whisker should be directed at that point, right? Right, -1, 2. So I'm going to draw it so it's kind of directed at that point right there. So there is the little whisker that has the proper slope. The heat just turned on, so it's blowing this thing around. Okay, so you can make the rest of these, right? And you could create an entire slope field. Okay. And I think they probably ask you to here, but we're not going to do the whole thing. Okay. Let's see. I'll put a few more in. If you look, they have some. This one has some symmetry to it, right? So, I mean, these will have the same slope up and down, except for opposite and sign. I think that's true with all these. Okay, so so what's the big deal with these? Okay, So I built this, slope field based on my differential equation strictly, right? And it's a very simple, easy peasy one. Now, if you look at this, we could actually solve this, right? This differential equation, you could separate variables and get an answer. So we're gonna do that in a second. But you could create a differential, from a differential equation, a slope field, where the diff-EQ, where the differential equation cannot, where the variables cannot be separated, if that makes sense, okay? So if where there's some that X and Y are so grafted in together, you can't separate them, okay? You could still make a slope field though, okay? You can make a slope field from any differential equation, okay? And then, so what, okay? Well, what you have, if you do, if you have a slope field, you have a picture of all the possible solutions, okay? You have a picture of all the possible solutions. So it is possible to sketch on the slope field a solution curve for which you can't find the equation, right? Kind of crazy, right? So it's possible to get a sketch of a solution curve that you can't find the equation for, okay? Yeah, okay? So this one we can, okay? So let's go ahead and let's see. If I know, let's see, if I know it goes through this point right here, so let's use this. If I know that my solution curve goes to this point, what I'm gonna do, I'm gonna draw on here, okay? So, all right. I'm gonna go back to your early childhood here, okay? Do you know who Winnie the Pooh is? Yes, you do. Pooh Bear, right? So, a game that he would play with Piglet in a river or stream is called Pooh Sticks, like Winnie the Pooh, Pooh Sticks, okay? And so what they do is they both get a stick, right? And they would go to a part in the stream and they would drop the stick in and then they would race the sticks. You've done this. You maybe didn't call it Pooh Sticks, but I'm sure you've done it, like tossed a leaf in or whatever and raced your friends or your siblings' boat down the river, right? And so where does that stick go? Well, it goes with the current, right? It goes with the current of the river, of the stream, okay? And so what we're gonna do here is we're gonna do the same thing. We're gonna play Pooh Sticks. We're gonna drop in our stick at our solution point. So if I know that this point is on my solution curve, I'm gonna drop it in right there, okay? Now where do I go? The whiskers are the current, okay? The whiskers on this slope field is the current of the river, okay? So I usually kind of go to the right first, okay? And so the current established by these whiskers. So I mean, the way the whisker directs you is where your Pooh stick's gonna go, okay? So here we go. So here like that, and all these along here are horizontal, right? They're kind of short here, but you can look, they're all horizontal along the y-axis. And so it should be horizontal there, okay? And goes up right here, and maybe something like this. Okay, and it's got to stop right there. Okay, now it may have actually, if I did this, it may have missed this. I had to go right through this point to -1. It maybe have missed a little bit. It might have gone a little bit more over here. And again, it's symmetrical. My slope field is symmetrical, so my solution curve should be symmetrical. And so this is a picture of the solution of this differential equation that goes through that point. Okay, so notice if I chose a different point, it would look different. Okay, So for example, if I chose this point right here, right, it would go up and be horizontal. It would hit this one over here and then go down and then stop. Again, it has to stop because if it keeps going, it's not a function, is it? Right? If it keeps going down into the bottom or goes all the way to the top and completes the whole rotation, it's not a function anymore. And remember, a solution to a differential equation is a function. Okay, so that's why I'm stopping here and here. Okay, and so you can see if your initial value for this slope field, if your initial value is up here above the x-axis, you're going to get the dome, right? You're going to get this dome thing. If your initial value is down here somewhere, you're going to get this smile. Okay, and the x-axis here is impenetrable because given the slope field, right, you would if you kept going, you would not have a function anymore. Okay, so these are called solution curves on a slope field. Okay, yes. Okay, so what we can do now is like, well, I did this pink one just based on my sketch, right? And my sketch, it's on the slope field, but I can find its equation because these are separable, right? I can do that. That's what I'm going to do next. So let's actually find what is the equation of this, right? What's the equation of this? Okay. So to do that, we will find the particular solution when it goes to the point -1, -2. Okay. Let's do it. So if I separate the variables, I'm just going to do it in one step. Is that okay? Since you guys are so fancy now. Okay. So here I've taken my differential equation and dx goes over here and I have to multiply both sides by y. So this is what I get when I separate the variables. Okay. So now I can integrate here. So 1/2 y squared -1/2 x squared plus c. Okay. So I just integrated after I separated the variables. Now I can figure out what c is, right? That's my habit, right? Again, Gary says you can do it at the end, and that's how his directions are written out. But I am a solve for c early guy. Okay, so I'm going to do that right now. So 1/2 -2 comes out. -1 goes in. Okay, so I've just plugged in -1 for x and -2 for y. Now what? So this would be 4, 1/2 of 4 is 2. This would be 1 times -1/2. I think my arithmetic is okay there so far. So I've moved this over here. So this would be 5/2. Is that right? Is C? Okay. All right. Oh, so go down a little bit. There we go. So 5/2 is C. So now my equation right here becomes 1/2 y squared -1/2 x squared plus 5/2. Okay, you good with that so far? Now, let's go ahead and solve for y now. So you have to double everything. So -x squared, that doubled is just 5, right? And then square root, so plus or minus. Okay, so now we have to put our weight down on positive or negative. Well, when I put in -1, I got to get out -2. So if I use the positive, there's no way to get out negative, right? So delete the positive root, right? So let's check. Let's put -1 in there. -1 times -1 is +1. Take the opposite of it. -1 plus 5 is 4. Square root of 4 is 2. The opposite of 2 is -2. So this is that. So we drew a picture of this without solving for this, right? So we are able on the slope field to draw my solution curve, to draw this without the benefit of having the equation. Whoa, how about that? All right, so I'm gonna go ahead and, I guess I can verify right here on my calculator, okay? So I'm gonna plug this in to my calculator, okay? And just to verify that it is what I said it is. I'll let you see it in a second here. Whoa. Okay. So I've entered in that, all right? Okay, and so now I'm gonna set up my window similar to the way this is set up. So it looks like we're going 3s, right? -3 to 3, about. Okay, here we go. Whoa, how about that? Pretty dang awesome, people, right? Isn't that pretty great? Okay, so if we would have used the other initial value, right? I also said, hey, what about 1, 1? Right? What about 1, 1? We would have gotten a different constant down here, right? So we'd have a different value here. And then down here, we'd probably pick the positive root because you want to get out a positive 1 because we're up in the northern hemisphere, right? And so, so that's how you would find the solution if you had a different initial value, okay? Pretty awesome, right? I mean, the slope fields are pretty great, okay? So again, and what was nice about this is we drew our solution curve, well, 2 of them, but the one that was down below, the pink one, and you don't really know how accurate it is, but we could actually solve the equation, solve the differential equation, excuse me, by separating the variables and solving for C, and that equation matched exactly what we just sketched. Okay, so it's pretty impressive that you can make a slope field and get a picture, create a picture playing poo sticks, right, of what the solution curve looks like without ever knowing what the curve's equation really is. Okay, the reason why we could do this because we could separate these variables, right? That's what we did down here. Okay, but you could do this same exercise, right? The same thing, create a slope field for a differential equation that where the variables are not separable. They are, it's complicated enough that they're intertwined together. You can't get them on their own sides, okay? You won't encounter any of those, right? And if you did, they wouldn't ask you to solve it. Does that make sense? They wouldn't ask you to find the general or particular solution. They would have you just work with it, maybe make a slope field and do some analysis, but without ever finding the equation, okay? So you can get a picture, you can create a slope field, get a picture of a particular solution curve without ever finding the particular solution equation, which is, I don't know, that was very, very dang cool, okay? So that's the introduction to a slope field, okay? So that's one type of question for the AP exam on slope fields. I'm gonna show you another one, okay? So sometimes you'll be asked to create one, and that's just plugging it in, right? I mean, so when you create a slope field, basically you're taking the equation, the differential equation, and you're just plugging in values. So it's a big old substitution arithmetic thing, okay? So how strict are they on having you do the exact whisker slopes, right? Well, that's not exactly 1, that's about 0.9. No points for you. That's not the point. Okay, they don't do that. So if you have a 0 slope, they should be horizontal, okay? We all kind of know what 1 looks. Well, if you have a slope of 2, it should be, steeper than 1. If you have a slope of 1/2, it should be shallower than 1. Okay, so if you make, it's a little bit like, do you remember doing lines of best fit, right? I mean, is there one exact one if you eyeball it? No, right? No. Is there one that's really the right one? Yeah, but if you get close enough, you're good. Okay, so that's probably the same, a nice analogy for it. Okay, so when you're making your slope fields, just try to be within reason. Okay, for your slopes. Okay, for your slope of your whiskers. All right. All right, so that's one type where you have to create one and maybe solve the differential equation. The other one is, well, here's a slope field. What diff EQ does it come from? That's multiple choice. You don't have to make it, you don't have to create it yourself. You'd have a bunch of options, okay? And so let's take a look at one of those questions, okay? And let me see. Okay, so this is actually example 6, if you want to look at page 168. Let me get set up here and then we'll look at it. Very high tech, right? I just was like, why don't you have this like digitally? Well, I guess I technically do, but I wanted to draw on it, right? And just mark it up. So I knew I could do it here. So that's why I don't have it in the digital form. All right. So if you look at example 6, okay, so here is the slope field right here. That's what I have on my whiteboard. And then it has a bunch of options, right? So which differential equation would give that slope field, okay? So I'm gonna write these up and we're gonna go through them, okay? So bear with me again, I'm gonna write all these up on my whiteboard, okay? I'm gonna pull this a little closer so my slope field is a bit bigger. Okay, so something I notice about my slope field, you notice that all these whiskers are positive in slope, okay? So no matter where they are, they're all positive, right? Every single whisker here has a positive slope, which means, you know, and again, y prime, this is the slope on the left-hand side. That means these expressions should be positive all the time, okay? So I'm gonna write that over here, okay? Whiskers all have positive slope, okay? And so what we're gonna do is go through these and say, would you always have positive slope? Would you, right? We're gonna go through one by one. And in general, like this is the way that I go through these types of questions. A lot of times, you know, on a multiple choice question, I'll just get, you know, I'll get the question and I'll just work through it and then find the answer. Here, I kind of go through these answers and cross things off, okay? Which is a different way of doing a multiple choice question. But for these, that's what I do. Because I can't just look at this and say, oh, the DFQ for this is blah, and then look for it over here. I can't do that, okay? So by and large, the way that I solve this one is by looking and noticing what's over here and putting down some clues and then going through these and crossing things off that are impossible, okay? So if I look here, this says that the slope is always equal to the x coordinate, right? If it's just plain old x, it means the slope really is the x coordinate. And so what you can do is kind of take a look here. Well, let's look right here. Right here, my x coordinate right there is -2. Is the slope right there -2? Heck no, right? That's not -2, right? The slope of this whisker is not -2. It's positive something. It might be +2. It's not -2. So I can cross that off. Okay? I can cross that first one off. Okay, the next one, y. Okay, this is saying that the slope is always equal to the y coordinate. Okay, so right here, so the y coordinate is 4. Could that be a slope of 4? Well, sure, I guess. That doesn't disqualify it. Here, my y coordinate is 0. Is that a slope of 0? No. Right? That's not a slope of 0. Here, my y coordinate is -3. Is that a slope of -3? No. Gone. Okay? Gone. Okay? So the next one is x minus y. It means the difference between the x and y coordinates. Okay? So you might have to kind of play around with this one a little bit. So let's look at some. So let's look right here. Right? That's 4, 4, right? So I put 4, 4 in here. That means y prime is 4 minus 4 is 0. Is the slope there, right? Is that 0? No, right? It's not. Okay, so that one's out of there too. Let's see, there's a question there. Oh, no. Okay, we're going. Okay, so now if I look at these down here, these expressions, both of these are going to be positive always, right? If you square a number and add 1, you're going to get something positive. So maybe you could have come down here immediately and said, okay, it's got to be one of these two, because all these have a chance of being positive in their overall value. These have no chance of being anything but positive, okay? So it's got to be D or E. Well, how do we choose which one it is? Okay, so let's pick some things, okay? So let's try this one right here, okay? Let's try that one. So let me pick some, let's pick this one here, 0, 0, right? 0, 0. 0, 0 would give me a slope of 1. Could that be a slope of 1? Yeah, that could be a slope of 1. Let's go down here. Go down there. So this would be -0, -4. Right, so the slope there, 0 goes nowhere, -4. Whoa, 17. Well, that's pretty dang steep, right? So I have no evidence here that this is wrong. Right, I have no evidence this is wrong. Let's try -4 with this one. Okay. So y prime is 1 plus 0 squared, or 1. So is that the slope of 1? There's no chance that that's the slope of 1. Right? No chance. So this one, gone. So your proper answer is D. Okay? So can you see that these take a while for me to figure out? Full disclosure. That these, when I'm given a slope field, they look really cool and they look really awesome, but they take me a while because I have to kind of do it almost by omission. I have to get rid of things that are wrong. What is right doesn't scream at me. It doesn't say I'm it, right? you kind of have to go through and see why the other ones are wrong, okay? Which isn't very time efficient, but that's the nature of these. And I've seen one question like this in the AP exam. I mean, slope fields would be on there for sure. I mean, I haven't ever seen an AP exam over the last several years that doesn't have a slope field on it, but you might be building them, okay? But there usually is maybe one question where you are given a slope field and you have to back out what is the differential equation that gives it, okay? Good one, right? Yeah. Okay. So your assignment, let me put it up here. And then, oh, one more word. Let's see. Now that this revised idea of the AP exam is kind of floating out there, it's like, what the heck? And so there are people out there a lot smarter than me who have some ideas already. And so I don't want to lay all those on you because right now it's kind of just speculation. At the end of next week, the College Board is going to come out with, here are the testing dates. That's, yes, plural. It recognizes that some of you might want to say, you know what, I want to take this as early as possible. I can't imagine it would be before May 5, right, our original date. But there's something like, man, I know the stuff now, and I'm going for it, right? I'm going to take it on May 5. And there's a later testing date as well to say, you know what, it's been a very weird time with the whole coronavirus. And so maybe I need more time to do some more studying because I haven't had the instruction that really leads me to knowing this stuff really well. And so therefore I'm going to take another 2 or 3 weeks to learn it better. So that is completely, that's up to you. Honestly, you can choose either option. And so once that becomes clear, again, that's next week, they'll say how many questions are on it, right? They know it's 45 minutes. They've said that, but they haven't said if it's 2 or 3 questions. And they haven't really said, how are you going to get your solutions to them? Right? That isn't there either yet. And so I know they're investing heavily in figuring this out because they want to be fair and they want to honor your hard work. And so they're doing their dangdest to figure something out. And so next week, I think it's April 4, is the day that they said they will have it figured out, okay? And then I will, of course, give that information to you. Of course I will, okay? So don't, I wouldn't spend a whole lot of time worrying about it because, worry doesn't get us very far anyway. So don't, speculate in your head, oh, it'll be 2 or 3 questions, and I'm worried that my phone won't work. Is a phone even something you can use? So don't worry about all that stuff right now, right? Shrug that off and just worry about, hey, what's in front of me right now? Slope fields is in front of me right now, so I'm going to do my best to learn those things. Okay, so that's where I put my weight down and not worry about what the test looks like. We'll figure it out soon enough, and then I will pass along the information. Okay, so here is your, can we talk about Calc BC? Oh, no, because I have no idea. No idea. Because, we're kind of shut down as far as that. But you know what? If I have a way to contact all of you non-seniors about DC, we can certainly talk about it. But things right now are just so weird about it, okay? Starting Wednesday, oh, yeah. So the College Board is trying to offer its support for all this. Where we are, so the College Board has a prescribed way, this is the first year ever, that they've kind of had a suggested progression to go through the material. And that's why some of you saw that units 1 through 7 will be covered on the AP test, but unit 8 will not be covered. And so they're doing it based on what their curricular framework looks like and their progression through the year. They allow teachers to do anything they want as long as you get there in time. Okay, so if you look at those videos, you might be seeing a video about something we haven't learned yet. So for example, we haven't learned what the derivative of tangent is yet, or the antiderivative of tangent is, or inverse tangent. So there might be some of those things on there because they've covered it already. And so you're welcome to look at those, absolutely. but just know that you might see some things on there that we haven't covered yet. And so don't be freaked out by it. We will get to those for sure, okay? All right. Here is your assignment. And if you copy off the section I gave you, there is what they call a tear out sheet, and that's supposed to be torn out of your textbook. And then because it has a place to put your slope fields, or it has a slope field on it. And so it's just for ease of use, instead of having to make a slope field on your own somewhere else. It gives you the grid upon which to put your whiskers, if that makes sense, okay? So, and then tomorrow we will do some AP questions about differential equations, and which includes slope fields, okay? Oh, sorry, my assignment's over here. Huh. That's it. 1 through 5, 9 and 10. Okay, so use that tear out sheet to do your stuff on, as suggested anyway. Okay. All right. Anything else, people? You're welcome. You're welcome. Are too damn long? What else you got going? Don't tell me you have a life. Whatever. All right. Love you guys, and I will see you tomorrow. Oh, and let's see. Let's see. Blah 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 blah. Mr. Templeton we'll have office hours today, and again, be there for 10 minutes. He said that no one showed up yesterday, which I was kind of surprised, since diffie Qs are kind of hard. And so he'll be there today for the first 10 minutes. If no one shows, he's going to jump. Okay. All right. Bye, people. Look for Schoology. Okay. I'll post everything, and yeah, and the invitation for tomorrow. So like that. Okay. The Zoom invitation. Okay. Bye, friends.